Welcome everyone. This will be the part 8 of the CUDA programming series, and in this part, there is no theory. We will be just introducing you, or you will be introduced to the platform called LeetGPU, where if you don't have any kernel or GPU access, or you don't want to run full kernels in Collab, this is a lead code type platform where you can practice various CUDA programming questions and various languages like CUDA, Triton, PyTorch, DSL, Mojo, and using various GPUs for simulation purposes. So we have around 6 problems to discuss. All of them will be easy. So after this, you can also go and try them on your own. Just finish this video. If you don't want to look at it, start solving it on your own. And if you are stuck somewhere, you can take the help of this again. So the first kernel that we need to write is the easiest one. It is vector addition. Uh, After you have watched the 7 parts of it, you can easily write it even in your sleep. So how the platform works is there is editor and the problems on the left. These are predefined things. So you don't have to change a lot of things here. If you want, you can change the threads per block or uh, invoking different types of grids of blocks. So right now it is 1D block, but if you want to invoke a 2D block grid as well, you can do that. So simple thing, we are finding the global index of the output element that we want to have the sum of A and B stored in. Then based on that index, we are just summing A and B and storing it in IDX by doing a bound check. Index should be less than n, right? Because we are invoking threads which will be more than or equal to the number of elements n. So n can be, let's say, 1000, and the number of threads you invoke is 1024. So the last 24 of them will not be working. They will be inactive threads. Moving on to the next kernel. Also, this video will be pretty short because we will be moving quickly through these kernels as they are pretty easy. You can also go and submit them. The next one is matrix transpose. We have seen this kernel in yesterday's video, if I remember correctly. Um, what we have is we are given a matrix A of rows and columns dimension, and we need to transpose it, and the transpose matrix should be equals to columns time rows in terms of dimensions. We are not allowed to use any external libraries of that sort. So if you look at the solutions or the submissions that I have made for this, let's check them. Yeah. So this is the first one, right? So this is the naive, the easiest one to um implement. You just find out the I and j of the input and replace the outputs j comma I element by inputs I comma j element. So this is the easiest kernel that you can have, and you can see you can experiment with different threads per block size, like 16 by 16. It worked fastest here. You can try to use 32 by 32 and see if the speed is improving or not. Now the fastest one that I got was this, where we are using the shared memory access as well as tiling to make it much faster. We are defining the tile size as 8. I have experimented with 16 and 32 as well, and the 8 one was the fastest. We are defining threads per block as tile by tile size. So it will be 8 by 8. Blocks per grid will be defined as the number of columns required plus tile minus 1 by tile. It is a standard way to do that. Moving on to the kernel, we are defining a shared memory of floats with size tile by tile plus 1. Tile plus 1 is to avoid the bank conflicts. We have discussed it, bank conflicts, earlier in a video. I don't remember which one. Then we are identifying which I comma j of the output we will be handling in this case, and then storing the thread index y and thread index x dimension in some variables for ease. Then we are storing these elements in the shared memory. So we are storing I comma j element of input in the shared memory at ty comma tx location. Now why we are doing that is, uh, in transpose, when we are doing transpose, the input read from the global memory is coalesced, but the output operation where we are storing the input elements is not coalesced. So instead of that, we first load all the elements in the shared memory in the coalesced manner. And when we are reading from the shared memory, it is uncoalesced. But since the read from shared memory is much, much faster than global memory, we achieve a significant speed boost, right? Then we are just syncing all of our threads. We are just making sure that all of these threads store their particular locations in the global memory in the shared memory. And after that, moving on to the last part of it, we are identifying the index I comma j in the output. You will observe that we have swapped the block indices and thread will remain the same as the I and j. So we have one block, let's say on the top left of input, then when we are transposing it, x and y dimension of that block will get swapped with each other. Then we are just doing a bound check since output matrix is m by n dimension, and then we are just storing it at out I comma out comma j index, and we are reading it from the shared memory. So we stored we stored the inputs I comma j element at ty comma tx location, and we will get it from tx comma ty because we are doing a transpose. So this is also an easy kernel. We have discussed it in detail, I guess, in yesterday's video, part 7, if I remember correctly. Moving on to the next one. This is color inversion. Let me check the fastest submission that I had. First, let's look at this one. And even this is the better one. This is much more easy, and even it is much, much faster than others. Or even if we are using some other thing like unsigned character 4 bytes, it is not giving a significant performance boost, so that we don't need to discuss it. So we are given an image which is represented as 1D array and RGB format. All of these elements are laid one after another in a linear fashion. So we have first pixel with all of these values from RGB and alpha, and then we have the second pixel with its RGB values and alpha. So 4 4 4, it is laid down like that, right? We are invoking the threads and blocks in a standard fashion. Then we are calculate the index of the pixel that we want to change. So there will be width times height number of pixels. Uh, then we are checking which pixel to change. Then we are doing a bound check on the pixel. So the index I should be less than height times width, which is the total number of pixels in the array. Then we are doing an offset. So input 4 times I should be equals to 255 minus input 4 times I. So what do we mean by inversion? As given in the question is we should subtract the RGB values from 255. So we are doing that here. The only little bit confusing part is why we are multiplying it by 4. So suppose the global index the thread gave is 0. So we are handling the 0th element, and by multiplying it by 4, we will handle input 0, 1 and 2 in the global memory. Then if the I value is 1, we are multiplying it by 4. So we will handle 4, 5 and 6th element in the global memory. Because each pixel contains around 4 information, 4 float values, uh, sorry, not float, in this case unsigned character values. We are shifting it by 4 each time to get to the appropriate location in the array. This is same like we do in matrix multiplication, where we multiply I by the number of columns when it is in row major format. We're just subtracting all of these values from 255. The last channel alpha needs to remain unchanged. We have no change there, and then we can submit it and it will run. Very easy kernel to write. Moving on to the next one. It is reverse array. It is a little bit difficult to understand, but very easy. So the first solution you can think of is we need to swap the first and last element, right? What we can have is we can invoke half of the number of threads. So suppose the arrays of length n, we can invoke let's say n by 2 number of threads. And if we get thread at I location, it will swap it with n minus I minus 1, which will be the last location in that case. So let's look at it. First, see this. We have defined threads per block as 256, and the blocks per grid will be defined as n times 2 times threads per block minus 1 divided by 2 times threads per block. Why are we multiplying it by 2? Because now we have said that each thread will handle two elements and swap them together. So we are just multiplying it by 2 here to invoke the appropriate number of blocks and threads. Then we are identifying the index of the elements which we want to swap, right? Then we are checking if it is less than n by 2. Then we are swapping the ith element of the input with n minus I minus 1th element. So this is also very easy. The only fundamental concept is each thread will handle two elements. So let's say I is 0, the I comes out to be 0, then the thread will swap 0 with n minus for, 1 element, which is the last one. Suppose I comes out to be 1, then we are swapping it with n minus 2 element. Suppose we are in block IDX 0, then all of these threads will be in linear fashion. They will be getting ordered and sorted together. Now, if the block IDX is 1 and let's say block dimension is 256, then we will be handling which element? It will be 256 times 1 times 2 to 512. We will start with 512th element. So the first block will handle elements from 0 to 5112. And the second block will handle starting from 5112 to 1024 and so on. So each block will handle 512 elements. That's why we are multiplying it by 2 here. Again, write it down yourself. It is very easy to understand once you get the hang of it, that each thread is handling two elements and both of those elements will be swapped together. That's why when we are invoking the number of threads, we are multiplying the threads per block by 2. And even when we are finding the when we are finding the global index of a thread, we are multiplying block dimension, block IDX by 2, because each block will handle two elements, twice as number of elements as before if we don't do it, if we don't do the multiplication by 2. The next one is ReLU. This is also very easy, as easy as vector addition. Simple. We are calculating the global index of the element to be changed. We are doing a bound check, and if it is greater than 0, we are storing the same value. If it is less than 0, we are replacing it by 0.00, right? 0 in floats. So yeah, very easy to understand. This will be the last one, which is matrix copy. I have implemented it as CUDA mem copy here. So we are given A and B. We want to copy A matrix into B, and it should match for all indices. So first, very easy way to do is use CUDA mem copy. We can define the destination as B, source as A, the size is as n times n, as size of float, and then we can define CUDA mem copy device to device. Other way to do it is, let's see, where was it? Yeah, very simple kernel. You find out the index that you want to copy, check the bounds. It should be less than n times n, which is the total number of elements. Then bi should be equals to ai. There is nothing else to be done here. So after this video, what you can do is go to LeetGPU and solve these 6 questions on your own without looking at the solutions. Then you will get a very pretty good idea and hang of the solution. So the most difficult one is the matrix transpose, but we have discussed in the earlier video. You will also find the code on the GitHub repo of these lectures for matrix transpose. But once you understand that, it will be very fulfilling. Okay. Thank you for watching this. This has been the part 8. Many more to come.